Hey there, welcome to the channel TechEd Kirsch, where we dive deep into hardware engineering, PCB design, software engineering, and artificial intelligence. In today's video, we're going to create the closed loop control of a buck converter using simulation-ready components in Altium Designer, and we'll simulate the design. This tutorial is ideal for both hardware engineers and students who are interested in learning about closed-loop control in practical design applications. And by the way, you can download a free trial of Altium Designer by clicking the link in the description below. All right, let's get started. All right, so the first step is to go to your project. If you have a workspace in Altium 365, you can go to your account and then create a file new project within your online workspace, or you can do it as a local project. I will go with my online workspace. It doesn't really make a difference. I will call this the buck converter closed loop 300 kilohertz. And we're going to take in 20 volts or regulate to around 3 volts on the output. Okay, 3 volts Vout. I would put a description in here, like if I'm working on a team, and checkmark version control and hit create. Okay, once you've created the project, you can right click on the project name, add new to project schematic, and the schematic gets added. So now we're going to do a control S to save this. This will be called the buck converter, same name. Let's remove the extension, hit enter, and that saves it. Okay, so the next step is to make sure to save everything. And then you can choose save to server, right? Save empty project. This is for the benefit of the team, okay? And also to be able to compare your different projects in version control. And if you want to manage your components as you add them to your schematic, you can use Octopart, log in, create an account, and set up your bill of materials as well from like an Excel spreadsheet for your reference designs, or you can look for components. There are tons and tons available. You can do parametric searches on these, and then they'll let you know whether they have models for these components or not, like the CAD models here. Super convenient. I always use Octopart for every design I'm working on to see everything all in one place as I build a new design or rework a reference design. So check out Octopart. Now we're going to make sure we have mixed simulation installed. You would do that by going to your profile, using extensions and updates, and installing mixed simulation. Once you do that and restart Altium, you can go to this new menu item called Simulate. Then you would start placing simulation generic components. Okay, that pulls up your panel for your components, and notice how you can drop down where you can choose all, choose simulation generic components, footprint symbols, but I'm going to go with this. Okay, so we're going to take in 12 volts into the circuit and then output around 3 volts, maybe 3.3 volts. That's the goal. And we use a feedback control loop to maintain that output voltage despite the load. So what you need is a voltage source, and that would be VSRC. VSRC, you place this down here. Now we need to place a ground. We need to place a power signal or power bar. And what I'll do is double click on here and rename it to plus 20 in the 20 volt range. Now you can do a control W to start wiring your schematic symbols, right? And that's just to demonstrate that process there. You can also go to place wire at the top and that will work. Okay, so now I'm going to copy my power symbol, place the plus 20V on this side. Okay, I need a switch to turn on the circuit for my power switching circuit, like my power stage. So you want to go with VD-MOS. So VD-MOS, MOSFET, it'll be an N-channel MOSFET, VD-MOS, there you go. You can rotate items with the space bar while you're placing them and after you've placed them as well. We need an inductor. So we'll place this inductor. You can hit the tab key to change the value before you place it. And from my calculations in my original design, I set this to 10 microhenry. I'm going to zoom in and place more components. We need some capacitors. So let's go to components, capacitor, double click. And you don't have to search for, like, you don't have to scroll to find these components. You can also search for them by just typing in the name, right? And it'll pull up. Okay, for our capacitors, we need this to be 220 microfarads. This capacitor 22 micro, and this one is 0.1 micro. We have the 1.6 ohm voltage or 1.6 ohm resistive load on the end here. So resistor, place that, spacebar to rotate it, and there we go. Now change this resistor to the 1.67. This will allow us to draw enough current to make sure this switching regulator is operating in its optimal range. Okay, adjust these devices. Okay, so now we need some more capacitors. I'm going to copy this capacitor with Control C, Control V to paste, and I can rotate that as I'm placing it. I'm doing the control loop here, so I'm going to paste. This is the compensator. Copy this resistor. So these three elements will make the compensator. I also need some other elements for my conditioning circuit, like a voltage divider on the output voltage from this circuit. Okay, and for this voltage divider, I need this to be 31.6 kilo ohms. This one at the bottom, 5.11 kilo ohms. And I need another capacitor around here, this region right here. And then a resistor, copy and paste this, rotate it. Okay, so this resistor in between the compensator capacitor area and this capacitor here, I would adjust these values. And then I need operational amplifier. So we go to components, op amp, double click on the op amp. I can rotate or flip this op amp horizontally with the X key and put this underneath the compensator circuit. I need a comparator as well eventually. But before we get to that, let me place my DC reference voltage for this op amp to compare the conditioned signal to my DC voltage. So let's go and we're going to look for VSRC again. Double click, place this on the positive reference node, hold down on this key item, or rather on this one, place ground power port. And then what else do we need? Okay, so we need our comparator and its own pulsed sawtooth waveform. So I'm going to go into components, comparator, flip that on the horizontally with the X key. Then I need my pulse voltage source. So what's cool is I can copy this source, place it, and I could have done that earlier, but I can double click on this source and then change it to a pulse source, then adjust its parameters and values to be a sawtooth waveform. That means it's going to have a long rise time. This will be 3.313 microseconds. The fall time, 10 nanoseconds, pretty sharp. Pulse width, I'll make this 10 nano as well. And for the period, we're switching at 300 kilohertz, so that'll be a 3.33 microsecond period for this waveform. Then for the pulse value, based on some calculations done in the earlier calculation stage, this comes out to 0.85 for our comparison. Okay. And then for our DC voltage here, this is going to be 0.696. Okay. Now we would also maybe have like a resistor in here, or a series resistor that goes into the FET gate. So this will be about 10 ohms. And then let's wire up the circuit. So to wire up the circuit, we're going to start with a Control W as a shortcut and then start making these connections. My negative terminal is going to go here to my sawtooth waveform. Copy this ground, place it here, make the wire connection. Then for the comparator, this would go into my compensator circuit. My capacitor here, resistance here. Oh, also this resistor, I didn't change or update this. I'm going to change this to 5.23 kilo ohms. Okay. And for this capacitor, set its value to 150 picofarad. Now, how do I know these values? These come from doing calculations for the compensator loop equation. Okay. So you need to do transfer function equations, analysis, and all that, and you'll be able to get these values. Moving forward, we'll continue wiring these components. And then the compensator, this leg would be on the negative part of this op amp. And this resistor I'll put here. Okay, this goes into the capacitor. Then I'll put this up through here. Okay. We have some more capacitors that would connect to ground. And what I'll do is copy this ground with Control C and Control V. Then what I can do here is copy both the wire and the ground and just stick those, paste those onto the capacitor bottoms. So then we have this going through the inductor, go to power supply. There you go. I recommend using a series resistor to help smooth out any sharp value changes in your circuit or your design. So I'm going to pick up this resistor, place it here. Now what's cool about Altium is you can drop your resistor or a component into your wire and it will not short across the terminals. It'll just get it in there for you. Okay, so then we have the we're going to change the series resistance to 1. Copy this equivalent series resistor, put it into our DC supply. Now, why am I doing this? This helps the SPICE simulation solver have an easier time solving its coming to a solution. So that's why I'm doing that. Okay, so the next thing we need is this op amp's output, which would be V control. V control would go into your comparator. I'm going to drop this comparator down a bit. Okay, and then this is our conditioning circuit to drop the output voltage down by. Now, this is a voltage mode controlled buck converter. Okay, why? Because we're conditioning the output voltage and then controlling based on the feedback going into our operational amplifier. Great. Going to drop that down some and drop this down some. And this looks fine by me. Now that our components are here, we need to go into annotation. So for annotating the schematic, we would go to Tools, Annotation, Annotate Schematics Quietly, and hit Yes. I also want to make sure that my DC power supply, we have a DC magnitude of 20. And what you can do is change this to a pulsed value that just stays on for a long time to better mimic or simulate the real behavior of a power supply, and also make it easier for a SPICE to simulate this thing. You generally don't want to have 0 time delay on starting a simulation. You want to have 100 nanoseconds time delay. And then your rise times, you kind of want them to be a little longer than 10 nanoseconds if they don't have to be. Okay, unless you're working with a chip or something that actually has that short rise time. And then for the pulse width, let's say this stays on for 3 seconds and it turns on and off every 5 seconds. Okay, but we're only going to run the simulation for about 5 milliseconds anyway, so this is fine. Then for the pulse value, this will be 20 volts on here on the high side, right? Okay, so this is looking good, and I'm going to label the nets. Let's save. To label my nets, I'd go to my net option and then choose net label. Then I already have this thing called V control, so I can put this on here, hit the tab key, and then we can call this VD. VD goes into the gate of the MOSFET, and then we have, you can hit tab again, and we can call this V out. V out we place on the output. I forgot to put my ground here, so I'm going to copy by Control C and paste with Control V. Now that a circuit is built, we are ready to simulate the design. Let's go into Simulation Dashboard. And what will happen is it will try to verify that you have models for all of your components in the design. For preparation, you can add a probe here if you want, or you can go straight to analysis, setup, and run. I'm going to do a transient analysis starting from 0 seconds to about 5 milliseconds. Put the M there. And then for the step, I'll leave that to do its own thing. I have the option to use initial conditions. This would skip the initial bias point. If I'm going to do that, I want to set some initial conditions. Like in my inductor, I would double click on this inductor, show more, and for the initial current, I'd say 0, because I'm assuming the circuit has been off for a long time, meaning the switch has not been turned on yet for a long time. Okay. Then I can use initial conditions and I would be able to run this. But I kind of want an output expression. I want this V out. And yeah, let's see how this V out operates. So let's click add. Then you click on this ellipses. Then you can go all, look for node voltages, choose V out, and then say, hey, this will be the output voltage. Okay, this would be on plot number 1, axis number 1. The units would be volts. The color I'll set to something like yellow, and then click create. Let's say I want another output expression. So for instance, the switching voltage, to see if this is actually switching on VD. So I would hit add and repeat this process. So click on my ellipses, node voltages, VD, V switch, switching, units are in volts. But the trick is you would put this on a new plot, axis number 1 of that new plot, and then you can set this color to pink or something like that. The next step is to run the simulation. And voila, we have our output. And this looks quite interesting. So I'm going to zoom in to my circuit here. And this is hitting around the 3 volts we were expecting for the circuit. Okay, and I can right click fit document. There are so many more things I can show you, like how to use probes on your simulation, how to view the simulation results, and using the simulation panel and sim data panel. But that would be for a next set of videos that I have planned and in store for you. All right, I'm going to go ahead and save these results and save my design. And you're good to go. And don't forget to save your project to your server for version control. Feel free to work with this project. The simulation files or this project will become available for you to download and modify for your own closed loop buck designs. All right, and that's it for today's tutorial on closed loop control of a buck converter in Altium Designer with circuit simulation. I hope you found this video informative and helpful. If you have any questions or feedback, feel free to leave a comment below. If you're interested in learning more about the design side of tech like hardware engineering, PCB design, circuit simulation, and artificial intelligence and prompt engineering, make sure you subscribe to this channel for more content like this. And don't forget to hit the notification bell to stay up to date with our best videos. Also, don't forget to check out the upcoming video series on Altium 365 Workspace, which can help you streamline your workflow and collaborate in the cloud with your team members. Thanks for watching, and I'll see you in the next video. Peace.